how do we know whether or not two variables are co-integrated? Because if they are co-integrated, then they share the same stochastic trend. And if they share the same stochastic trend, then we can take the difference between these two variables, and we would end up with a stationary variable, which is the difference. Well, the three ways to determine whether or not we have co-integration between these two variables is, well, the first one is to use economic theory. Then you have to know the theories in the market in which you have data, and you can use this theory to say something about the relationship between different variables. So, for example, in our example of the 3-month and the 10-year interest rates, then if we look at the expectations theory, it says that whether or not you're investing at a 10-year horizon or a 3-month horizon and rolling this investment over, then and reinvesting, then you should end up in expectation with the same amount of returns. And therefore, the expectations theory suggests that these two interest rates, they are co-integrated, because you can't they can't diverge from each other, because then people would invest in the security which gave the highest interest rate on in expectation, and not invest in the security which provides the lower returns. And the second method is to graph the time series. So in our example, we graphed the time series of y and x in the same plot, and we found that they were quite similar in the long run. And this would lead us to believe that these two time series, they share the same stochastic trend. You can also have a statistical or perform a statistical test of co-integration. And what you do now is that if the x variable and the y variable are having a or they are I1, then let's see, I1, then you can test whether or not these are co-integrated by taking the difference, which is yt minus a number, a scaling of the xt. And if this new variable, this difference variable, is stationary, then these two series, they are co-integrated. If these two series are not co-integrated, then this difference would be non-stationary. And you already know how to test for non-stationarity, and you can do that with a unit root test. For example, the augmented Dickey-Fuller test. And in this case, we have two cases, and that is whether this scaling parameter is known or unknown. The first case is if this scaling parameter theta is known. For example, in our case with the 10-year interest rate, which is one variable, and the 3-month interest rate, which is another variable. This is yt, this is xt, for example. And here we, from theory, we assume that this theta, to make up this difference, is equal to 1. So we can just take the difference between the 10-year and the 3-month interest rate, and we would get a new variable, which is z of t. And in this case, theta was set equal to 1 because of the underlying financial theory. But you can make this difference with any known value of theta according to which variables you investigate. And this difference is a new variable called zt, and this zt can be tested for a unit root by the Dickey-Fuller or the augmented Dickey-Fuller statistic. And the critical value for this test, when theta is known, is the critical values for the ADF test. So then you would just use this table to investigate whether or not your ADF statistic, your Dickey-Fuller statistic, is more negative than the critical value. If it's not, then you would assume that this difference, this z of t, is non-stationary. If this ADF statistic then is more negative than this critical value, then you would assume that the difference is stationary. On the other hand, if you do not have any theory to guide you as to what is the value of this scaling parameter, theta, then you have to estimate it before we can apply the unit root test. And this is quite easily done by estimating this regression. Yt equals an intercept. This is the intercept, the alpha, plus the theta, which is the slope on the x variable, which is coincidentally the scaling parameter, plus an error term. And as we used z for the difference, we should not use that for this. We should just use u of t, okay, which is the error term. So then you can actually create the difference variable, which is, as always, z of t equals y of t minus the estimated slope here on the x of t. So this is the hopefully stationary difference between these two time series. So this would be the Engel-Granger ADF test. One matter of importance is that since this theta is estimated, we are not entirely certain of its value. And this is causing us to need different critical values for the Engle-Granger ADF statistic compared to the ordinary ADF statistic test. So in our case, we are going to look at only the case in which we have one x variable in our equation. So up here, we only have one x variable. However, it is possible to have a stationary relationship between several of these x variables and the y variable. So a combination of the y variable and, for example, theta 1 of xt plus theta 2 of x2t, so this is x1t, and x2t plus the error term. So here we are assuming that the difference between the y variable and theta 1 of the x1 variable and theta 2 of the x2 variable would be stationary. So our difference in this case would be y of t minus theta 1 of x1 minus theta 2 of x2. So this would be our new variable, and this variable z of t could be tested for non-stationarity, but then we would use the critical value around the or in the second row, because here we would have two x variables. However, in our course, we are only going to consider the cases in which we have one y variable and one x variable. So then you would, for example, if you have a 5% significance level, you would compare the ADF statistic or the Engle-Granger ADF statistic to the critical value of negative 3.41. And if the statistic is more negative than this critical value, you would reject the null hypothesis of non-stationarity. And if you reject the null hypothesis, then you have a stationary difference, which means that the z of t variable is stationary, and you can work with this variable.